Welcome to my channel MAKAUT. In this video, I am going to discuss about some important questions which are in past coming in the MAKAUT examination, that is the fourth semester examination, that is the in the digital electronics. So as you know that your exam is in your doorstep and the syllabus is not covered yet, so I am trying to give some solution of the previous year's important question that may come in your exam. And obviously if I cover at least 50% or 60% of syllabus, then it is obvious that you must get 50%, that is the 50 marks from that 10 videos. Okay, means I am trying to cover the entire syllabus, at least 50 to 60% syllabus in the next 10 videos. Okay, so let's start. 2018 question, digital electronics. First question is implement a full adder using a 2:1 multiplexer, and second question, that is the design a full adder using minimum number of NAND gate. Both are coming from the full adder circuit, that is the combinational circuit. That you know that in the digital electronics there are two kinds of circuit. One is the combinational circuit and another is the sequential circuit. So sequential circuit and combinational circuit, what is that? So you know it. If you want to know it, then just definition. By definition, you know that the combinational circuit, that is the output of the circuit is only dependent upon the present input. Okay, that means that there is no dependence on the output in the previous output. Okay, and in the sequential circuit the output depends on the present input as well as the previous output. It means that adder, what kind of circuit a adder is. Okay, so adder, if you consider adder is nothing but a combinational circuit. Okay, why? I can solve it directly, but to solve this type of question, this type of full adder using multiplexer or the full adder using the NAND gate, basically these are the nothing but the combinational circuit using the multiplexer and the NAND gates. This type of question definitely come. You will get at least both of the questions in this coming examination, I think, because either it may be by 2:1 multiplexer, or it may be by 4:1 multiplexer, or it may be by 8:1 multiplexer. But this is where 2:1 multiplexer is very much important because it is bit complicated. Okay, now so adder circuit is a combinational circuit. Adder means that can add the numbers. Okay, so adder is nothing but if you want to add 1 and 0. So what is your result? The result is nothing but the 1. 1 plus 0, 1. 0 plus 1 if you want to add, then it becomes 1. 0 plus 0 if you add, then the result is 0. And if you want to add 1 plus 1, then it becomes 0. And there is some carry is 1. There is 1, 0. Okay, so you know all these things, I think. So now, so these 1 0 or 0 1 or 0 0 or 1 1, whatever it is, if you want to add, then you can, these are how many bits number? This is a 1 bit number. So you can add this number by using a half adder, and the output cannot depend upon the previous input as well as the previous output. Okay, but okay, and if you want to add a not a 1 bit number, it may be a 2 bit number. A 2 bit number may be 1 0 0 and 1 1 0. Then it becomes 0 plus 0 is equal to 0. There is no carry. 0 plus 1 is equal to 1. There is no carry. But 1 plus 1 is equal to 0 and there is some carry. So to solve these things, so solve the 3-bit number. This is the 3-bit number. We will use the full adder. This is the difference between the full and half adder. Okay. Now, what is sequential circuit? Sequential circuit is nothing but an output which is dependent upon the input also. That means if there is a counter, that is counter is count something. That is there is a gate and there is a circuit present over here. There is a counter. That means if you somebody enters through this gate, then the counter becomes 0 to 1, then 1 to 2, then 2 to 3, then 3 to 4. As much as people are enter through this gate, the counter will increase by 1. That means when there is no men enter in through this gate, then the counter is 0. When number first person is entering through this gate, then the counter becomes 0 plus 1 is nothing but the 1. Again, the second member is when entering through the gate, then 1 plus 1 is equal to 2. It means that the second time the output is dependent upon the previous output. The third time the output is the dependent on the previous output. So these are nothing but the counter is nothing but a sequential circuit. Now, what is half adder and what is full adder? I can discuss briefly. Okay. So what is half adder? Half adder basically nothing but so we can take the half adder in a rectangular box. This is a half adder. Now there is a two input line. One is you can say that A, another is you can say that B. This is nothing but the first bit number, and this is nothing but input of second bit number. Okay, and the output is two. One is nothing but the sum, and another is nothing but the carry. Okay, that is the carry output. Okay, it means when 1 and 1 you add, enter 1 and 0, you enter 1 as A and B as 0, then sum is 1 and carry is 0. When enter A as 0, B as 1, then sum is 1 and B as 0. When enter 0 and 0, then sum and carry both are 0. When you enter A as 1 and B as 1, then the sum is 1 and carry is also 1. So this is nothing but the half adder circuit. Now, the half adder circuit is used to add the single bit number, and it does not take carry from the previous sum. Okay. Now, if you elaborately do the circuit diagram of the half adder circuit, then you have to draw its truth table. So what are the input? What inputs are A and B, and what are the output? Output are S and C. Okay, A stands for sum, C stands for carry. So when A becomes 0 0, B becomes 0, then 0 1, then 1 0, 1 0 and 1 1. These four combinations we can give. Then the sum for 0 and 0, the sum is 0 and the carry is 0. For the 0 and 1, the sum is 1 and carry is again 0. For 1 and 0, the sum is 1 and carry is again 0. But for 1 and 1, the sum is 0 and carry is 1. It means this is your truth table for the half adder circuit. Now if so, what is the expression for S? So if you know, means if you consider the A, B and S, forget about the C first. Now you want to express the S, so you treat the input A and B and output as S. So S will be, so if you look at this A, B and S table, then what you get? You get that this is a output of the XOR gate. Means when they are in the input side, when there is an odd number of 1, then the output is 1. Here there is no 1, so it is 0. Here it is an odd number, there is one number of 1, then it is a 1. Here is also one single 1, that is the odd number of 1 get 1. But here there is a even number of 1, that is first 1 and second, there is 2 1 is present, so the output is 0. So this is nothing but a XOR gate. Okay, so S become A XOR B. This is your expression for the XOR. Okay, now if you want to take the expression for carry, what is carry output? Carry output become, now you consider this A and B, this table, and forget about this S and consider this C table. So for 0 0 it is 0, For 0 1 it is 0, for 1 0 it is 0, for 1 1 it is 0. Means when the both inputs are high, then the output is high. It means that carry expression we can write that this is nothing but the truth table for AND gate. So we can write that A and B is the output. So what is the expression for the half adder? The expression for half adder is S is equal to A XOR B and carry is equal to A and B. Now you can easily draw the circuit. So what are the inputs? A and B. So A and B are input. This is your XOR gate. This is your A. This is your B. A and B is there. Then you can get A XOR B. That is nothing but the S. Now, what is the expression for C, A, B, and C? It is the nothing but an AND gate. So you take one AND gate and make this output as A and B, that is nothing but the C. So this is your internal circuit diagram of half adder circuit. It means if you just erase it, because we have to make it larger. So if the lines, input lines are this, then, and if you draw this entire logic gate circuit inside a rectangular box, then this is nothing but the half adder with the input A and B, and the output is S and C. These are the C output, this is the S output. You got about the half adder circuit. Now consider the full adder circuit. Now, so I can erase it because I have less amount of space over here. So it is not a black or green board. If it is a black or green board, then I can easily make these two half adder and full adder in the two part in simultaneously in the same board, but we have to erase it. Okay, now, so taking in pen. Now the full adder circuit, it is the logical circuit that adds the three single bit number, and this is nothing but the full adder. That is, the full adder is able to add the single bit number. That means we have 1 0 0 and 1 1 0. So this 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, no carry, but 1 plus 1 is equal to 0, and there is a carry 1. It means that for this we need the previous carry for addition. Okay, now consider the expression elaborately. So this is your full adder circuit. Full adder circuit. Now the input is A, B and Ci. This is A, this is B, and this is nothing but the Ci. That is the carry input, because if in this place if there is a 1, then this 1 plus 1 becomes 0 and 1 is carry, then 1 plus 1 0 and 1 carry. That means that there is some provision for taking the carry for addition in the 3-bit number. We need some provision for taking the carry in the consideration as the input, and the output become, obviously the output is sum and carry. This is sum, this is carry out. Okay, so it means there are 3 input. As there are 3 input, that means 3-bit number. So the how many possible number of if you make the table A, B and carry input and output as S and CO, then how many possible inputs are there? So 2 to the power 3, because 3 is the input, that is the 8 possible inputs are there. It means if you write the inputs, then it becomes 0 0 0 0 0 1 1 1 1, then again 0 0 1 1, again 0 0, again 1 1, and in the third it becomes carry is 0 1 0 1 0 1 0 1. Now if you add this number, then sum should be, so 0 0 1 1 0 1 0 0 1, and the carry is 0 0 0, then 1 0, then 1 1 and 1. This is the most important table for this entire, to solve this two entire question. This is the most important table, because for full adder circuit, uh, if you want to draw a full adder circuit using any kind of gates or the multiplexer, you need this, and you have to know the Carnot map. Okay, so this is the combinations of inputs and the carry and sum output. Okay, so I can make it in the box. So this is the important for entire video. Okay, now what is the sum? So we can make a Carnot map, or we can solve it by the Boolean algebra. If we can make it through a Carnot map, then the Carnot map will be it's a B and Ci are the input and S is the output. So if you want to solve through the Carnot map, the S will be, so for solving the S, you have to write S over here, then A and B Ci. Okay, so there are 8 inputs. It means the Carnot map is like this. So here it become 0 0 0 1 1 1 and 1 0. Okay, so the Carnot map become, this is 0 and 1, and this is 0 0 0 1 1 1 and 1 0, and this is column number 1 is 0 number cell, 1 2 number cell, 3 4 5 6 and 7 number cell. Okay, write it down, 0 number cell, 1 2 3 4 5 6 and 7, that is 8 combination. So so for S, as I want to solve the S, it means that the S is in the position of 1, in the position of 2 and 4 and 7, that is the, and position 1 and 2 and 4 and 7, and other are keep vacant. So if you consider this Carnot map, you see, you wondering that you cannot make any group, because we cannot make the group in the like this diagonal. We cannot make a diagonal group. We can make a 2 4 8 and 16 group, okay, in the square or rectangular form. So this is a very important configuration called the checkerboard configuration. You write it CHECK here, checkerboard configuration, and for that the output become nothing but the A XOR B XOR Ci. Okay, now I can make it through the Boolean algebra also. How we can make it go through Boolean algebra? So the expression is, so if you consider this, forget about this CO, you consider A, B, C, I and S. So A has become, so it is in the sum of product from S become, so 0 means bar and 1 means not bar. So A, B, C, I, A, B, C, I, everything has the bar because all are 0, plus A bar, B bar, Ci, sorry, this is in a, sorry, this is for S, we are calculating S. So S is in this position, S is in this position, that is the 1, 2, 4 and 7. 1, 2, 4 and 7. That means we get the 4 expression. What is that? For 1, it is A bar, B bar, Ci. So S become A bar, B bar, Ci plus second position is A bar, B, Ci bar, A bar, B, Ci bar, because 0 means bar and 1 means not bar. Then 1 is A, B bar, Ci bar, A, B bar, Ci bar plus last one is A, B, Ci. A, B and Ci. These are the expression. Now solve it. So take A from the first point, B bar Ci plus B Ci bar. This is very known expression. Then you take A over here, then B bar Ci bar plus B Ci. Okay, so this become A into A and B XOR Ci plus A and B XOR Ci whole bar. It becomes A XOR B XOR Ci. So whatever, you can solve it through Carnot map or you can solve it through the through the De Morgan's theorem. We can solve it. Well, sorry, Boolean algebra. We can solve it. Now this is the expression for S. The S is nothing but A bar, A XOR B XOR C. Now what is the expression for S? Sorry, C. So we can, for C we can make, so we can erase it this adder also. So we can make the adder circuit, the C expression, then we can make the adder circuit. So again we can draw one Carnot map. This Carnot map is calculation for C output. This is A, this is B and Ci, and this is for C calculation. Now write down this A as 0 and 1, this is 0, 0, 0, 1, 1, 1 and 1, 0. So in the position for Ci, where it is 1, it is the position 3, position 5, 6 and 7. 3, 5, 6 and 7. So make the number first. So this is 0, 1, 2, 3, 4, 5, 6 and 7. It means that at the position 3, 5, 6 and 7 we get it. 3, 5, 6 and 7. We get the 1. So now make the group in the Carnot map. So we can make 3 group. One is this group by 1 taking 2, 1, another is this group, taking these two one, and another is we cannot take the 3 1. If there is a 4 consecutive one, we can take the 4 consecutive one, so we can take the 3. This one is the 1 and 1, the yellow is the first group, the red is the second group, and the green is the third group. So now writing the C output, CO, is become CO, it become, so in the first case for group 1, the expression is here the B and CI both are 1, so it is B CI, because they are not changing. B and C is same, A is 0, A is 1, A is changing, so we cannot consider A, we can consider only B and Ci. Now for group 2, that is the for red color, what is that expression? It is the, here A is 1, A is 1, A is not changing, here B is 1, here B is 1, here Ci is 1, here Ci is 0, means A is not changing and Bi is also not changing, because here Bi is, B is, sorry, not Bi, it is B. B is 1 over here, B is 1 over here, Ci is 1, Ci is 0. That is, Ci is changing, but B is not changing. Here in this line, A is 1. So A and B is the expression. And third is, there is the green one. The green one expression is, here A is not changing, A is intact, and here in these two, B is 0, B is 1, that is B is changes. Here Ci is 1, Ci is 1, that is Ci is not changes, the ACI. This is the expression for C output. So if we want to make a full adder circuit, then the output become S and Ci. Now take the next page. Yes, now you can draw the S. First you write down S as what? A XOR B XOR Ci. And for C, it become A Ci, C carry input, plus AB plus B Ci. Okay, now you can design the gate. So now take one XOR gate. One XOR gate for A, and this is your A input and this is your B input. A input and B input. So the output become A XOR B. Now you just fed it in the another XOR gate and take Ci as the second input of the second XOR gate. This is your Ci. Then the output become A XOR B XOR Ci. This is nothing but the S. So here we get the output S. Now we are going to take the ACI, AB and BCI, and all are ANDed. So we can take 3 AND gate. Okay. Here one AND gate, another AND gate is here, and this is your third AND gate. Okay, now first one is ACI. That is the one input is from A, another input is from Ci. So this is ACI. Now for second one, it is AB. So one input will coming from one input. My pen is disturbing day by day. So this is your one input A, and this is your one input B. So the output is A, B, and third one it is B and Ci. So taking this from B, just changing the color, we are taking it from B over here, and this is your CI over here. So this is your BCI. Now they are ORed, that is the ACI or AB or BCI. That means if you fed this in a OR gate, then you can get the, this is your OR gate, and the expression is C is nothing but the ACI plus AB plus BCI. This is nothing but the C. Okay, so this is all about the full adder circuit. Now coming to the question, we have to know about the multiplexer. Okay, so now considering what is multiplexer, now we can say it as MUX, that is the multiplexer circuit. Okay, so what is multiplexer? It is a combinational logic circuit that select one input at a time out of many input. That means there are many input, we can, but there is some selector line that can select only one input at a time and select it to the output line, and it is simply nothing but a data selector. That means if it is a multiplexer, 2:1 multiplexer or 4:1, whatever it is, so these are the input lines like this. Now this is your output Y. This is the inputs are written as I0, I1, I2, dot dot dot, like IN. Okay, n minus 1, not n minus 1. So these are the input lines. Now there is a selector. Selector is nothing but, it is nothing but a dialer. So this is your dialer. This is I1, I2, I3, I4, I5, I6, like this. So when this dialer is touches I0, then output is like that. If the dialer is coming to I2 or I3, if the dialer is coming through I3, then the output is changes. Like this, the dialer can change and the output can be changed. So it can, very simple circuit, and it is easily handleable, and obviously it is in a, we can implement it in a single chip. If you want to make it with a NAND gate, there are so many gates you need. So it is nowadays it is in single chip, so we can easily implement it in a circuit. So Y become I0 or Y become I3 or Y become I4, whatever it is, depending upon the where the select line is selected. That means we have to move the selector to change the output. So how we can change the selector? The selector can be changed. The selector is nothing but the select line. We can change the selector as, first we consider how many selector we can select. So the multiplexer is 2:1 multiplexer, or it is 4:1 multiplexer, or it is 8:1 multiplexer. Okay, so for 2:1 multiplexer, the select line is only one select line is there, and for 4:1 multiplexer, the two select line is there, and for 8:1 multiplexer, three select line is there. Okay, so 2:1 means 2 is the input and 1 is the output. 4 is the input and 1 is the output. 8 is the input and 1 is the output. It means one thing you should clear, that in the multiplexer, whatever it is, or it may be 16:1 multiplexer, or it may be 32:1 multiplexer. So whatever the input is, but the output line is always 1. So for 16:1 multiplexer, the number of input is 16. So first we consider 2 input as 2 to the power 1 8, sorry, 4 is equal to 4, we consider the input lines. 4 is equal to 2 to the power 2, 8 is equal to 2 to the power 3, 16 is equal to 2 to the power 4, 32 is equal to 2 to the power 5, like this. That means n is equal to 2 to the power m. The m is nothing but the select line, and n is nothing but the input. So when 2 is input, it becomes 2 to the power 1. So select line is 1. When it is 4 is to 1 multiplexer, 4 is input. So 2 to the power 2 is there. So 2 that is the select line is S0 and S1. Okay. So when it is 8, it is 2 to the power 3. That means 3 is your select line. Select lines are S0, S1 and S2, like this. Okay. So for we can make the question is we have to make the full adder circuit using a 2:1 multiplexer. So you focused on the 2:1 multiplexer. How the 2:1 multiplexer? What is 2:1 multiplexer is? So now we know the multiplexer. In the multiplexer, the select line is a rectangular size, rectangular shaped chip. So this is your S0 because there is only one select line. The inputs are I0 and I1, and the output is only Y. Okay, this is your 2:1 MUX marks. Okay, so now if you want to make, or you can, okay, another thing, you can symbolize this multiplexer in this way also. This is your 2:1 marks, and this is your select line S. Okay, now if you want to draw the for two input multiplexer, the truth table is for S naught and Y. So when S naught is 0, that means when S naught is 0, then the select line is, the output is I naught, and when S naught is 1, the select line is I1. Okay, let me make it very clear. If for that we want to take one 4:1 multiplexer. Okay, this is your 4:1 marks. Then the output is obviously 1Y. The input line is 4, I0, I1, I2 and I3. The output line is, the select line is 2, 2 to the power 4, it is 2, that is the S1 and S0. Okay, now you can make the, depending on the select line, the input is selected, and depending on this selected input, the output is there. So the combination is S0, S1, S0 and Y. Okay, how the, so 4 input, that means the combination is 0 0, 0 1, 1 0 and 1 1. Okay, so when 0 0 is selected, the Y should be 0, sorry, not 0, it is I0. When 0 1 is selected, Y should be I1. When 1 0 is selected, it becomes I2, and when 1 1 is selected, it becomes I3. That means if you write the expression for Y become S1 bar, S0 bar and I naught plus S1 bar, S0 and I1 plus S1 S0 bar, I2 plus S1 S0 I3. This is the, this is how, when so when S is 1 is 0 and S2 is S0 is 0, then the dialer is here. When the S1 is 0 and S2 is 1, then their dialer is at I2, and depending upon that Y is I2. Like I1 I2, like this we can select the input, that is the select, depending upon the input in the select line we can take the output as, that is the output is reflected in the output side. Okay, so if you draw the diagram for the, for this S0 and Y is means the 2:1 multiplexer, it is quite easy that this is your S1 line, this is your S0 line, and these two are the lines, and these two are the not, that means if 0 and 1 line. Okay, now sorry, we are going to draw the only the 2:1 multiplexer, so it is quite easy, but the 4:1 multiplexer is quite critical. So here it is the S0 and Y, so it becomes very easy. So you draw S0, and from here we can note it by like this, that is the S0 bar. And if you, this is your I0, so when I0 is connected, so what is the output of this? So output of the 2:1 multiplexer is, that is the S0 bar I0 plus S0 I1. So S0 bar I0 means S0 bar ended with I0, so S0 bar ended with I0. So this is your AND gate, and here is your S0 and I1, that is the, if it is I1, so this is your I1 and this is your S0, these two are ANDed. So here output is S0 bar I0, here it is S0 I1, is it? Now both are ORed with a OR gate, that means this is your diagram for the 2:1 mask. 2:1 mask. Okay, this is quite easy. Now we can implement the full adder circuit by the this mask. So what should we do now? Now again we can write the expression for, that is the truth table for full adder circuit. Okay, so for what are the full adder circuit? So the inputs are A, B, Ci, S and C output. So 0, 0, 0, 0, 1, 1, 1, 1. It becomes 0, 0. It becomes 1, 1. Again 0, 0. Again 1, 1. Here Ci is the 0, 1, 0, 1, 0, 1 and 0, 1. The output is the 0, 1, 1, 0, 1, 0, 0, 1, and Ci is the 0, 0, 0, 0, 0, 0, then 1, 0, 1, 1, 1. Okay, just A and A plus B, whatever the answer is, that is added with Ci, then you can get S. And if there is carry, then carry become 1, and if there is no carry, carry becomes 0. That is A plus B. 0 plus 0 is 0. Again 0 plus 0 is equal to 0. Sum is 0, carry is 0. 0 plus 0 is 0. 0 plus 1 is equal to 1, but carry is 0, 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1, carry is 0. 0 plus 1 is equal to 1. 1 plus 1 is equal to 0, carry is 1. 1 plus 0 is equal to 1. 1 plus 0 is equal to 1, carry is 0. 1 plus 0 is equal to 1, 1 plus 1 is equal to 0, carry is 1, 1 plus 1 is equal to 0, 0 plus 0 is equal to 0, 1 plus 1 is equal to 0, carry is 1, and 0 plus 0 is equal to 0. 1 plus 1 is equal to 1 and carry is 0. Sorry, 1 plus 1 is equal to 0, carry is 1. So 0 plus 1 is equal to 1, and as carry is 1 written over here. So this is nothing but the truth table for full adder circuit. You have to know it very well, because to solve any kind of full adder circuit problem, you should know this truth table. And you keep on your mind one thing, that the question will arise. The question will not be like that the what is full adder circuit, draw a full adder circuit diagram. There is some combinational circuit. You have to make a combinational circuit using some gate or some another combinational circuit. That is the main motto of the digital electronics subject, because we have to design the gates, design the circuits through gate, through multiplexer, through demultiplexer, through adder, through subtractor. So you have to know Carnot map very well, and you have to know that you have to write the truth table very well. Okay, now here we have to implement 2:1 mask. So here one is 2:1 marks. For it is 2:1 marks for S. So as it is 2:1 marks, so the input is 2 and the output is, and the select line is 1. So this is 2:1 and it is for S. And you draw another 2:1 marks to solve the carry, and obviously there is another select line. So we can make a select line anyone. You can make a select line A, you can make a select line B, or you can make a select line Ci. So when you make a select line A, taking A as select line. Okay. Now, so if we consider if we draw the circuit of that is the nothing but the S, that is the sum, then you consider the select line as A becomes 0 or A become 1. So for the first 4 case, A becomes 0. Okay. So for these first 4 case, A becomes 0, and for that A becomes 0, what are the inputs? The remaining inputs are B and C, and the output we consider as S. So we can deal with these 4 tables. So when A is 0, now consider the B, Ci and S. Now you can write B, Ci and S. So B 0 0 1 1, Ci is 0 1 0 1, and S is 0 1 1 0. Okay. So if you clearly, this table shows, if you look this table very thoroughly, then you see one thing, that this table represents some logic gate. So this is your input B and Ci, and S is your output. So taking A as select line and A as 0, if you consider B and Ci is a input and S is a output, so this is nothing but the XOR gate. That is this is B, this is Ci, and this is S 0 0 0 0 1 1 1 0 1, means when only one, there is the odd number of 1 is present, then the output is 1. So B and C are XORed. So it means if we draw one XOR gate over here, this is B and this is Ci, then the output is S. Now A is 0, we can conclude our circuit. Now when A is 1, so when A is 1, that means in these last 4 cases, when A is 1, then consider B and C I as input and S as output. It means, so write down B and Ci. So when here I can write it through the green color. So B is 0, it is 0, it is 1 1, it is 0 1 0 1, and the output is 1 0 0 1. It means that is that for 0 0 it is 1, for 1 0 or 0 1 it is 0, for 1 0 it is 1 0, and for 1 1 it is 0. That means in the previous case the inputs are same, but the output is 1 becomes 0, 0 become 1, 1 become 0 become 1, and 1 becomes 0. The both the inputs are same. BI 0 0 B 0 0 0 0 1 1 1 1, CI 1 0 0 1 1 0 0 1 1. That means in the both two cases, when whether whatever the A is 0 or 1, here we can write it as 1. Whether whatever the 0 A is 0 or 1, the this is 1. So whatever the A is 0 or 1, the output, once it is first case 0 1 1 0 and second case 1 0 0 1, that means it is reversed. It means it is nothing but a X NOR gate. That is the XOR. This is your XOR, then this is your NOT gate, then it becomes XOR gate. That means the output is like this. So this is your B, this is Ci, and this is S. It means if you connect one NOT gate over here, then what ban gayi? That is the B and Ci. When the A select line is 0, it becomes S, and when the A is 1, the B and Ci, it becomes. So when A is 0, that is the B and Ci works as a XOR gate. When A is 1, then B and Ci is XNOR, and it becomes S. So this is the circuit diagram for S. Now consider the C. So if you consider the C in the same case, so you just erase that S line and we consider only the C line. Okay, C as the output line. It means we are considering A as a select line and B and A as a select line and B and Ci is a input line. Okay, now again draw this. So here first case Ci 0 0 0 1 and it is 0 1 1 1. Okay, now for carry, so if you compare B, Ci and Co, so 0 0 1 1 0 1 0 1, carry becomes 0 0 0 1. So clearly you see that this is nothing but a circuit for a AND gate. For when both the inputs are high, then the output is high. So 0 0 0 0 1 0 1 0 0 and 1 1 1. So it is nothing but a AND gate. So when for A is equal to 0 select line, when a is equal to 0, this is your, so we have to draw one AND gate over here. This is B and this is CI. Okay, now consider the second part. That means the when B is, so just change the color. B again 0011 0011, C is 0101, same input, but C carry becomes 0111, means whether there is only one active, whether there is only one high, then the output is high. It means it is a nothing but a OR gate. So when A is 0, it is a AND gate is selected. When A is equal to 1, then BCI is OR gate is selected. It means there is no way to draw the same in the we can draw a OR gate over here and make this like make the connection like this. So this is your B and CI. When A is 0, then B and CI is working as an AND gate, and when A is 1, then B and C is working as a OR gate. Okay, so this is how we can change the using the two multiplexer. We can make a full adder circuit. Okay, now the so for S it becomes A plus XOR B XOR CI, and for C naught it becomes ACI plus AB plus BCI. Depending upon these two, we can make this truth table, and from this truth table we are making 2:1 multiplexer by through which we can make a full adder circuit. Now coming to the next question. Next question is design a full adder circuit with a minimum number of NAND bit. Okay, this is I think you can solve it by yourself. हाँ मैंने फिर भी हम ये करते रहे क्योंकि logic gate, you know the logic gate from class 12. So NAND gate is what? So full adder by minimum number of NAND gate. Okay, so you know that we can implement a XOR gate by XOR gate can be designed by using 4 NAND gate. Okay, it means that so we can, so first we have to write the AS, and we need to make the circuit of full adder circuit. That means the output will become AS is equal to A XOR B XOR CI, and C become A and B or CI A B. Okay, now we can use 3 input XOR or 2 input XOR. Okay, so we are using 2 input XOR. Okay, now to make it, just first we make the S. Okay, so what should we do? We should first draw the XOR gate using NAND gate. Okay, so how can we make the XOR gate? So here for S it is the only XOR operation is there. So we are taking 4 NAND gate. One, here it is second NAND gate. You just see the position of the NAND gate which you are taking. So here the input is A and B. Okay, now the A is fed with one of this second NAND gate, and for B it is fed to the third NAND gate. Now changing the color, the output of this NAND gate is fed to the first and second NAND gate. Okay, so this is your A, this is your A B bar, this is your B. So this the output become A and AB bar whole bar, and these output become B and AB bar whole bar. Now this is your Y. So output is we can solve the output. So the output become Y is equal to A dot AB bar whole bar into B dot AB bar whole bar. So it becomes A dot A bar whole bar, and as it is named, so the whole bar. Okay, now we can split it. A AB this become B this, and it becomes OR with B AB like this. Again it becomes A dot, that means A ANDed AB bar plus B ANDed AB bar. So we can write AB bar become A bar plus B bar plus B, again A bar plus B bar. So it becomes A bar plus B bar plus B bar plus B bar. So it becomes, you can write AB bar plus BA bar, or you can write it as A XOR B. So we can implement one XOR gate using 4 NAND gate. Now coming to the full diagram. Now so we can erase it. Okay, so we can erase this thing and make this diagram. From here we can make the entire circuit. Okay, so here output is A XOR B. Okay, so the output become A XOR B. Now this is for AB. Now take one CI over here, take one NAND gate over here, and there we can take one we can make this somehow over here. So this is A XOR B. Now we can make this as in another NAND gate, where we can take one CI it becomes A XOR B into Ci bar. Okay, now now we can take here another gate, another NAND gate here, and this output is fed over here. So, and whatever the output is, that output is fed over here. Again, from here we can take another NAND gate, and the C is also taken over here. Now these both are connected through this NAND gate, and we can get A plus B, means A XOR B XOR Ci. It means this is a XOR for A XOR B. So A XOR B is an input of this 4 NAND gate as well as one Ci. Then we get the A XOR B XOR Ci as sum. So sum is there. Now carry. What is carry? Carry is A dot B, A and B plus Ci into A XOR B. Now keep one minute notation, that means that A, we take A dot B. Okay, so if we take A dot B in this point, if we take A XOR B Ci and A dot B, so here this expression is A XOR B dot Ci, means this expression is, the output is over here. So if we take the output from here, then the input is nothing but the A, this input is A XOR B and Ci, and as there is a bar, so it has a bar. Now if we take one input from here, then this is also nothing but the A dot B bar, and as both are so this is nothing but the input of A XOR B and Ci, and it is A and B bar. So both are, this is your NAND gate, so we can make one entire NOT operation. So if we make this, solve this, then this become A dot B plus Ci into A XOR B. So this is nothing but the C. So here we can get the sum as A XOR B XOR Ci, and from here we can get the output as A and B plus Ci and A XOR B. So by this diagram, so this is your Ci and this is your A, this is your B. So if you ask that what is inside a full adder circuit, or if you want to make a NAND if you want to make a full adder circuit through a NAND gate, then if you need 1 2 3 4 5 6 7 8 and 9 NAND gate, and this is the minimum. So first of all we are ANDed A and B, that means the A XOR B, by the through the 4 NAND gate, then Ci taking Ci as another input as into the another NAND gate, and A XOR B in the another input of the NAND gate. We are getting the A XOR B XOR Ci. That means that these these four NAND gate are making the A XOR B and Ci as XOR. Okay, and these four NAND gate are used by making A XOR B. So A XOR B and Ci is the input of these four NAND gate, and we are getting A XOR B XOR Ci. And here we are getting A and B bar that is fed with the in a NAND gate, ninth NAND gate, and here we are getting A XOR B and Ci bar that is feeding in that NAND gate as another input, and we are getting the whole bar, and whole bar means it is the output is A dot B, A and B plus Ci and A XOR B. So this is the entire circuit diagram for a full adder circuit using the minimum number of, that is the 9 number of NAND gate. So this is the solution for 2018 detailed electronic circuit, and this is nothing but the from the full adder circuit. Okay, now we are in the next video we will discuss about some Carnot map and some binary conversion, and if possible we can make some multiplexer, or you just I'm trying to cover the 60-70% syllabus, but your homework is you have to make a full adder circuit using 4:1 multiplexer and 8:1 multiplexer. If you keep watching my video, share and subscribe my channel to get the various kinds of solution from digital electronics and the other subjects, and please comment me if you are able to solve the full adder circuit using 4:1 and 8:1 multiplexer or not. If I'm getting the time, then I can solve that thing also. In the next video we can discuss about the implementation, the K-map and uh, some subtractor. So adder is covered today, and in the next day we will cover the subtractor circuit and some K-map problem. Okay, so keep watching on my video. Please share and subscribe my channel.